In this video, we'll practice solving transient material balances by going through the solution for problem 2 of the Chapter 10 Lecture Examples worksheet, which you can find on the home page of Canvas. In this problem, the premise is that we have some sort of tank that's being filled with water. And then at some point, this tank develops a leak that progressively gets worse over time. We're given both the rate of the water going into the tank, which is constant, and also the rate of the leak, which is linear with respect to time. For part 1 of this problem, it asks us to develop a material balance on the tank and use it to obtain an expression of dV dt, which is a differential equation describing the volume of water in the tank at any time after the leak has formed. Part 1 also asks us to identify an initial condition for this differential equation. In part 2 of the problem, we want to then solve the differential equation so that we have an expression describing v of t, and then it asks us to sketch a plot of the volume versus time. At this point, I want you to pause the video, and I want you to use the information in this problem statement to develop a process flow diagram for this process. Before we go on, I just want to clear up any confusion and identify that in the drawing here, there's actually an error. This should be 0.050 meters cubed per second. Okay, and that's the value we're going to use as we go through the solution of the problem. In any case, with the exception of that, all the other information in the problem is accurate. And so based on this information, we could develop a process flow diagram that looks like the one here. And so in this process flow diagram, what we have is a tank that's being filled with water initially at a rate of 0.050 meters cubed per second. Okay? At time 0, we say that the tank develops a leak, and the rate of that leak is 0.0025 times time, t here, and that also has units of meters cubed per second. We're also told that the volume of water in the tank initially at the time that the leak springs is 1.2 meters cubed, while the overall volume of the tank is 12.5 meters cubed. Okay? And so now that we have all this information, the problem statement asks us, it wants us to ultimately solve for the volume of the tank, volume of water in the tank as a function of time. Okay? And so to approach this problem, to get all the way up to being able to solve for the volume, the first step, or the next thing that we need to do, is we should write out what our general material balance equation is and then simplify that. So let's next deal with this general material balance, and then simplify it. Okay? Okay, so our general material balance, as you know, is just A is equal to I minus O plus G minus C. Okay? For this process, we're just filling a tank with water, right? There's no reaction going on. And in any case, if we think in terms of mass, right, based on the conservation of mass, you can't generate or consume any mass. And so what that means is that our generation and consumption terms are just equal to 0. And so in our material balance, what we're left with is an accumulation term, an input term, and an output term. So let's identify what each of these remaining terms are. So for accumulation, we're not dealing with a steady state system anymore, right? So for our accumulation term, we could write it as dm dt, where the m stands for mass. But in this problem, we're dealing with volumes here. And so we want to rewrite this mass term in terms of the volume of water in the tank. And the way we could get that is because we know that the relationship for a liquid between mass and volume is that the mass is just equal to the density of the liquid times the volume of the liquid. And I'll write that the volume is a function of t for extra emphasis. Okay. Now, since we're dealing with liquid water and, we're not told that there's any giant temperature changes or anything, what we can assume is that our density of the water here is just a constant. And since it's a constant, that means we could pull it outside of the derivative. And so what we end up with is just rho density times dV dt. And so this is our accumulation term. For the input, it's the same sort of thing. What our input mass is just going to be equal to the density of the water times the volumetric flow rate of the water that's incoming. And the output is just going to be equal to the density times the flow rate of water going out, or the leak. Now that we've identified each of these terms, we could plug them into our material balance equation. And so we have the accumulation term is equal to the input term minus the output term. All these densities can be canceled out. And for the right hand side, we could actually just now plug in what our volumetric flow rate in and our volumetric flow rate out are. So here and this. I'm not going to write out the units just to keep this, make the equation less busy, but we have to remember that the 0.050 here and the negative 0.0025 here are in units of meters cubed per second. In any case, we could now just write out clearly what our differential equation is. Okay? And at this point, we should also write out what our initial condition is as well. Okay? Alright, and so if we go back to our process flow diagram, we need to identify, what our initial condition is. Right? And so, in this case, what we're talking about is the problem statement tells us that once the leak forms, the volume of water in the tank is equal to 1.2 meters cubed. And so that means that this V is equal to 1.2 should be our initial condition, not the volume of the tank, right? I just want to emphasize that. And so that tells us that at time is equal to 0, the V in our differential equation, which is describing the volume of water in the tank and not just the tank volume, that V is going to be equal to 1.2 meters cubed. Okay, and so this is our answer for part A. Let's now proceed to part B, which ultimately asks us to solve this differential equation and develop an expression describing V of t. So, start with part B. I'll rewrite our differential equation here. Okay. 0.0025t. Okay. And so, if we want to solve this differential equation, we need to make sure that it's in a format that is solvable based on the analytical tools that we know so far. Okay? And so, if you remember back to the review videos where I reviewed how to solve differential equations using that were separable, what we need to do is we need to cast our differential equation in terms of a separable equation. And what I mean by that is we need to, if we want to solve this differential equation using the separable method, we need to identify the parts of the differential equation that represent some function of v and some function of g of t, right? These are the two variables that are described by our differential equation. And so, at this point, what I want you to do is to pause the video, and I want you to identify the parts of the differential equation that we could say represent a function, or f of e, and the parts of the differential equation that would represent g of t. looking at this differential equation, what we can say is on the right hand side we have that 0.050 minus 0.0025t. And so we could just say that the g of t in our expression is this, minus 0.0025t. And for the f of v, there's nothing on the right hand side that is an explicit function of the volume. So we could just say that our f of v is just 1. Now that we have identified what our f of v and our g of t are, let's move all the v stuff to the left-hand side and then all the t stuff to the right-hand side. And so on the left-hand side, we're just going to have dv over 1, which is just dv. And on the right-hand side, we're going to put in parentheses this part, and then outside the parentheses, I'm going to put the dt. Okay? Once we have it in this form, to solve it, let's just integrate. And for me personally, what I like to do, rather than using definite integrals where I integrate from the initial condition to some arbitrary t, the way I like doing it is actually I first do an indefinite integral. Okay? And so if I do an indefinite integral, for the left-hand side, if I integrate dv, what I get is just volume. Okay? And if I do an indefinite integral of the right-hand side, what I'll get is 0.050 t, and then 0.0025 t squared over 2. But since I'm doing an indefinite integral, what I also need to remember is that there's going to be some sort of unknown constant that develops here. And so the reason I like doing indefinite integrals is because for me, I find it personally easier to manage all the unknown constants that develop. All right, but you're welcome to do a definite integral. Ultimately, your solution should be the same, whether you do indefinite integrals or definite integrals. But in any case, I did an indefinite integral, so for the rest of this video, I'm going to follow at least the workflow that I use to solve these problems. Okay? And so, in any case, we have an expression that describes the volume as a function of t, but we still have this sort of unknown constant here on the right-hand side. To figure out what that constant is, at this point, I now want to apply the initial condition. And so our initial condition, says that the volume of the tank, or the volume of the water in the tank, is equal to 1.2 meters cubed at time is equal to 0. Okay? So let's apply this condition to our equation here. So v at time is equal to 0 is equal to 1.2. And on the right-hand side, what we're going to do is we're going to plug in 0 into our t. Alright, so we have a 0 there, and 0.0025 over 2 times 0 squared, and then we have our unknown constant. Okay, and so that goes away, and that goes away, and so ultimately what we end up with is that our unknown constant is just equal to 1.2. Okay, and so if I go to the next page here, we could now write our v of t expression, our volume, is going to be equal to 1.2 plus 0.050 t minus, and I'm just going to write out what 0.0025 divided by 2 is. It's this. Well, that's multiplied by t squared. And so this is the expression we have for v of t. But at this point, before we box in the answer, I want to make sure that this equation that we derived is actually correct. And so at this point, what I want you to think about is, I want you to think about how we could actually make sure that the equation we derived is correct. So pause the video here and think about that. To determine if our v of t expression is correct, what we should do, so check equation, what we should do here is we should just see if this equation satisfies both our initial condition and also dv dt expression that we started with. Okay? And so first let's check the initial condition. Right? And so we were told that v of t at 0 is equal to 1.2. Right? And so on the right hand side, let's plug in that. So 1.2 plus 0.05 times 0 minus 0.00125 times 0 squared gets us 1.2. So our equation does satisfy the initial condition, so let's check that off. Let's now see if it satisfies the derivative, the dv dt expression. And so if we take the derivative of our equation that we derived here, right, what we get is, let's go term by term. The derivative of 1.2, which is a constant, is 0. Alright, so we'll put 0 there. The derivative of the second term, 0.050t, it just gives us back 0.05. And then the derivative of the third term, right, we bring down the 2 and we multiply it by the coefficient. So we get 0.025t. Right? And so if I just kind of simplify it again here, and we'll see that this is the same exact differential equation that we started with when we simplified our material balance. And so our equation does satisfy that derivative statement. So at this point, we can now be confident that this v of t expression that we derived is correct. Now the final part of the problem asks us to plot what v of t looks like over time. But to do that, so far we've just kind of worked with math, right? We just solved a differential equation. But at this point, if we want to be able to plot what v of t looks like, let's try thinking, what this equation means. So, what does this equation physically mean? So let's go back up to the top here. Alright? And so in our equation, we have v is equal to 1.2 plus 0.050t minus 0.00125t squared. Okay? So right now that just looks like math. But let's go on the right hand side, let's explore one by one what each of these terms physically mean. And so this 1.2 term here, right? Now the reason that showed up is because that came from our initial condition, where we said that the volume of water in the tank at time is equal to 0 is 1.2. And so this term is basically describing volume of water in tank when the leak starts. Alright? For the second term, this equation is describing the rate of the water that's filling the tank, right? And so over time, we saw that the rate was constant. And so what that means is that as time increases, the amount of water that came into the tank, if there was no leak, that would be increasing linearly with time, right? filling of tank. Right? And this last term here, this part was describing the leak of the tank, right? And we could see that this part here, it's not linear. It's actually t squared. And so as time increases, that leak rate is also going to increase. Okay? And so if we want to, develop more of a physical picture of, what this equation is describing, what we could do is we could start thinking about, what does this equation look like at various limits? And by that I mean, all right, let's start thinking about what would this equation look like if t here was really small, pretty close to 0. Okay? And so let's think of what happens at small t. Okay? And so if t is really small, the filling term is going to be kind of small because it's multiplied by t here. But the leak term is going to be even smaller, right? So let's say t was a value less than 1, right? And so if t is less than 1, if we square it, it's going to be even smaller, right? And so here, even though the filling of the tank value is pretty small, the leak term is going to be even smaller, all right? And so physically what that means for us is that the fill here is faster than the leak. And so if the fill is faster than the leak, or a larger value, that's going to tell us that the volume of water in our tank is going to get bigger. Or mathematically, that dV dt is positive, greater than 0. Okay. Let's now flip it around. Let's now think about what's happening at large t. Okay? And so here, at large t, our fill term is multiplied by t, so now it's going to be larger. But the leak term is multiplied by t squared. So if t is much greater than 1, t squared is going to be much bigger than t. Okay? And so that tells us that at large t, our leak term is going to dominate. It's going to be faster than the fill. And so if the leak term is larger than the fill term by magnitude, that tells us that the volume of water in our tank is now going to get smaller. Right? Or dV dt is going to be negative. Okay? And so at small t, our volume is getting bigger, and at larger t's, the volume is getting smaller. And so based on that logic, right, if we go from getting bigger to getting smaller, that means that at some point, there's going to be a maximum value of our volume. Okay? And so when we're doing this sketch, right, we're going to want to see some sort of maximum value, some sort of peak. Okay? But right now, how can we figure out where that peak occurs? Right? There's nothing in the problem statement that gave us an idea of when that peak occurs. And so, how can we figure that out? So at this point, pause the video and think about, how can we figure out when the time where the volume is at its maximum? To figure out when the volume reaches its maximum, when that time occurs, what you need to do is actually just think back to your Calculus 2 class. And anytime you deal with derivatives and you want to find the maximum, what you just need to do is set your derivative equal to 0. And so if we want to find when our maximum occurs, we just need to set dV dt equal to 0 and then find out what time that corresponds to. So let's go through that. So for dV dt, we know, based on either just taking the derivative of our VAT expression, or even just using the differential equation we derived at the beginning, we know that dV dt is equal to this, And if we want to find the time in which the maximum volume occurs, so T max, we just set our derivative equal to 0. Okay? And so what we could do is we could just, based on this, we could just solve for T max just through algebra. And so if we solve for T max, what we get is that the T max is equal to 20 seconds. So this tells us that 20 seconds after the leak forms, that's when the volume of water in the tank is at its highest. Okay? Alright, and then to figure out what that V max is, we can then go to our V of T expression and then plug in T max. And so here I'll write V max is equal to 1.2 plus 0.050 times T max minus 0.00125 T max squared. And if we plug in T max, we find that the maximum volume of water in the tank is 1.7. Okay? The other thing we need to figure out, right, is, if after T max the leak rate becomes much greater than the fill rate and the volume gets smaller, eventually all the water in the tank is going to run out. And so V is going to be equal to 0. Okay? And so at this point, I want you to think about, how can we figure out the time in which that occurs? How can we figure out at what time does the volume of water in the tank become empty? Okay? So pause the video right now and think about how we could figure that out. To figure out when the tank becomes empty of water, what we could do is we could just set our V of T expression equal to 0 and figure out what time that corresponds to. So can also figure out when tank is empty by setting V of T, or I'll call this V of T final, equal to 0. Okay? And so if we go back to our V of T expression, set it equal to 0, and then plug in on the right hand side. So 0, 0, 5. So let's say this time corresponds to T fin, or T empty, you could call it as well. 2.5 T fin squared. Okay? And then what you could do is just solve for T fin. We have a quadratic equation here. So you'll end up with two solutions. And so the solutions that you end up with are negative 17 seconds or 57. Okay? In the real world, we can't have negative time, and so we'll just ignore that solution. And so we could say that our T final is just equal to 57 seconds. That's the time when the tank becomes empty. Okay? Alright, and so now that we've kind of used our V of T expression to figure out what are the limits of, or the behavior of the volume of water in the tank, we can now just go out and sketch it. And so here are my axes. Every time you draw axes, you need to immediately start labeling them. So the y-axis is the volume as a function of time, and this is going to be in units of meters cubed. And the x-axis here is going to be time in units of seconds. Okay, I'm going to write 0 here, 57 seconds here. This will be about 20 seconds. Okay, right here I'll write 1.3, and up here I'll write 1.7. Okay. Alright, and so from our equation, what we could do is we could just start pointing out, at time is equal to 0, we know that the volume of water in our tank is 1.3. At 20 seconds, we know that the volume of water is at its maximum. It's at 1.7. And then at 57 seconds, we know the volume of water in the tank is 0. It's empty. Okay? And so if we want to sketch the behavior of v of t as a function of time, we just need to basically just connect the dots. And so here and here, right? Our v of t equation is a quadratic equation, so we kind of know what a quadratic equation should look like here. All right? And so, just by solving this differential equation, this gives us a very powerful tool for predicting and understanding, and tracking what the volume of water in this tank is at any time that we want.